In this tutorial, you will learn how to create a basic PBR render. We'll use the result from the previous tutorial and implement shadow, PBR lighting, radiance, and irradiance. You will touch base with all the necessary building blocks that you need to create your own render. By the end of this tutorial, you will have a PBR renderer capable to render a large array of material. The first thing that you will be implementing is shadow map. Shadow map can basically be divided into three steps. The first step is to create the depth pass, then draw the scene from a probe point of view, use the off-screen data that we rendered, the depth data, and project it onto our scene. To create the depth pass, we will need to add a new render layer. We will need to add the object that will act as caster and receiver. We are going to need to add also a probe object to simulate the light, the sun in this case, point of view. We're going to create a depth attachment that we will connect to that probe to store the depth data. We will have to create a draw script to call the front face of the caster and receiver to only focus on the back face that will be projected onto the scene. Finally, we will write a depth material and a shader just to store the depth data. At the end of this step, we will draw the scene from the probe point of view and render the data into the depth attachment. Once we have that off-screen data, we will use that result to then project the shadow onto the scene. We will connect that depth texture to our PBR material, and we will do the necessary update to our PBR shader. So this is basically the way we left our scene in the previous tutorial. We are now going to start adding shadow to it. The first thing we're going to do, we're going to go under scene properties and we're going to add a new render layer, basically creating a new render pass. I'm going to click add layer and I'm going to call it shadow, and as soon as I enable its drawing, you can see that now something is not right. Basically, it's because I am drawing my scene with my checker and then I'm drawing the scene with the shadow. I actually want to do the opposite. I first want to draw the shadow, draw the scene from the projector point of view, from my probe point of view, and then draw my actual scene projecting the shadow onto it. So what I'm going to do to remedy to this situation, I'm simply going to drag and drop my render layer on top, which means that the shadow now will be rendered first and then my camera. And this is exactly the kind of mechanism that you can implement in your own render layer. Based on the render pass order, you can reorder and your render layer in a way, in a fashion that will actually execute the good rendering sequence that you're looking to create. Now, I got my first render layer that is now shadow, and the goal is now to move those receiver and shadow caster to my shadow render layer. I will not move my cube map here that is basically just there to simulate the horizon. It will never receive or cast any shadow. I'm only interested in my checkers here. So to do that, I'm going to enter edit mode for my second render layer, Shift and 2, and I am going to select the object that I want to move to my shadow render layer. To do this, I'm going to go under the object properties and relations. You can see that there's render layers here, and it is currently, my floor is currently only connected to Untitled, which means that it will only be drawn on the Untitled render layer. And now I want it to also be drawn onto the shadow render layers. So I'm going to click, and now if I go in my first render layer, which is shadow, you can see that my floor is now there. As you might have noticed, it is actually there, but it is not drawing anything. It does not have any instruction that tell this floor how to draw on this render layer. And we are going to actually fix that in a minute. Let's continue to bring our receiver and caster to the shadow render layer. I can be more productive instead of selecting them one by one and clicking, the render layer check. I can simply do a multi-selection and then go on selection, add to render layer, and shadow to do that in batch. And as I go back to my shadow render layer, they are now all placed on it. ready to be instructed to draw actually something. To actually project the shadow, I'm going to need to have a probe object that is basically allowing me to capture the scene from a certain point of view. To do this, I'm going to go in Object and Add to Render Layer. I do not want to add it on all the render layer in the current scene. I only want to add it on this render layer that I'm editing right now. So Add to Render Layer, and I'm going to go under Probe, and now I got basically two option Planner and Environment. Planner is just basically a quad, and Environment will be a cube map. If I wanted to do a omnidirectional light shadow, I will use a cube map that is going to allow me to render the environment from front, back, left, right, top, and bottom. But I'm basically looking at creating a directional shadow, so basically I'm going to select Planner. I'm going to change my shaded mode to be wireframe so I can see actually the debug draw of my object at the same time. And now what I want to do is to move this probe to be at the exact same location and use the exact same rotation as my sunlight here that it's in my second render layer basically. So what I want to do first to do that efficiently, I'm going to move my 3D cursor to be at the same location as my sun here. And to do this, I'm going to go under Object and then Cursor to Active. That is going to move the 3D cursor to the active object. Back to my shadow scene, I am going to select now my projector and I'm going to do the inverse operation. I'm going to go on Object and now Active to Cursor, which is going to move it. I'm going to tweak its rotation, which is basically 65 on the X and 135 on the Z, and now my probe is located at the exact same location as my sun and look exactly down the way this sunlight is actually looking at. Now I'm going to start tweaking some probe properties. With my probe selected, I have now access to the probe properties of that probe. I'm going to go there and click on it. The type Planner, we know that already. Dynamic, I'm going to click yes, and this will allow me to capture at a specific rate my scene. If it was set to disable, which means that basically the probe is static, I can assign an asset. Let's say that I have already pre-rendered my depth, and I can simply include it here, and that's all there is to it. But I'm interested in dynamically updating my capture, so I'm going to click Enable, and that will allow me to set now a bunch of settings that are basically related to the view of that specific probe. You can see that the phase type is -Z. This is the zero rotation looking down at the Z axis, and my face is actually enabled. And now I'm going to change the update rate. By default it is 60 Hertz, and I'm going to put it at 0 Hertz, which means every frame you're going to update and recapture the scene from the probe point of view each and every frame. I'm going to also set my debug draw to be able to get some sort of feedback while I'm editing, some visualization of, in this case, my depth while I'm editing my render layer. The next step is basically to set the camera settings, which right now we don't have enough setup. I'm going to leave that for later. We're going to move on to the frame buffer settings, and what I want to fill in right now is the depth attachment. I'm going to need to create a depth attachment and connect that depth to my probe, and I'm going to receive debug draw on it. So what I'm going to do, I'm going to go under my library textures folder, and I'm going to create a new asset, texture, and it will be an attachment. I am going to call it shadow, and the internal format of that texture attachment, I'm going to select depth because that's what I'm interested in. I'm going to leave all the other options as they are, and I'm going to create it. Now I'm going to connect my shadow to my depth slot. And as soon as I do that, you can see that now I start to receive some feedback. It is black because it is not actually drawing anything yet. We need to specify that information in a moment. The last thing that we're going to specify is the render layer of that probe. That probe will actually capture which render layer. And In this case, we have shadow, so we want to actually capture what is draw on the render layer shadow. If you had multiple probe placed on a specific render layer, you can always toggle them on and off based on what exactly you're trying to achieve. So basically, in this case, we only have one anyway, so we're going to enable it to render on the shadow render layer. And if we go back to our scene properties here, we can see that now, since we have a probe on our render layer, we can see that here we have the hint that this render layer will be a probe pass. The system is analyzing that basically if we compare to our other render layer, the one that is drawing those checker, it have a camera. So basically we have the mode that will be used to draw that render layer. In this case, a camera. We can also have a material that is applied on it if we want to have like, if we want the scene to, the render layer to be using an example, a compute shader. Or we have the option to have camera, compute shader, or if none of these are actually set and there is a probe, it will analyze that this render layer will be used as a probe pass and it will render all the probes that are located on this render layer with the ability to actually capture that specific render layer. The next thing that I want to do, since I got that all set up, what I want to do is actually, I am not interested in drawing the front face of my object. I'm only interested in drawing the back face, and this is what will be projected in onto my scene to actually draw my shadow. So for that, I'm going to create a script, and since my probe is a drawable object, it actually can respond to the on draw and on display events, which means that on draw is just about to draw and send comment to the GPU, and on display is right after it's done drawing. So the on draw event callback will be the most optimal event to use to actually tell my GPU to actually call the front face and only keep the back face visible, which is basically the opposite of what is set by default. By default, only draw the front face and exclude the back face that the camera cannot see. So to do that, I'm going to create a new script. So I'm going to go back in my library and double click on my root, and I'm going to call this new asset group scripts. And under scripts, I'm going to create a new scripts from the asset menu, new script, and I'm going to call it, let's say, call face. I'm going to create it, and now I'm going to open and create a new code editor under script and call face. I got basically the default header that is generated for me, but I want to use actually nodes to do that one. So I'm going to click the button that enable nodes, which give me access to the node editor, and I'm going to hit the space bar, and I'm going to go search my on draw event. The next thing that I want to do is to invert that, to set that call face mode. So I'm going to go search my call face node, and I'm going to ensure that the mode is set to front, which is the first on the list. That's exactly what I want. And the next one, I'm going to want to clear my depth texture every frame. Every time I'm drawing, I want to clear it before to have a fresh one, just like we did in a previous tutorial. Since I don't have a color buffer or a stencil buffer for this one, just the depth will do. Next step is to actually connect now, to actually connect the script to our probe. So to do this, with my probe selected, I'm going to access the object properties this time, and I'm going to create a new scripting thread. And I am going to simply drag and drop my new script with the slot, the asset slot here. And if I double check an event, it means that, oh, I detect that I have an on draw event and it is checked. So it means that it's okay. This object will actually respond to that specific event. Go back to my scene. Now at this point, we already talked about it, that once I'm in shaded mode, I basically have access to these objects, but they are not drawing anything. And this is what I'm going to do right now. The next step is to actually draw send those objects on screen. And to do this, I am going to create a new material to actually write my depth. So in my materials folder, I'm going to create a new asset material, and I'm going to call it write depth. And every material needs to basically have a shader connected to it. I'm going to put my material for editing. So I'm going to access the material properties and drag and drop my new material here. So I'm going to have access to its property to edit. I could have also simply selected from the list here. And what it's missing here is a shader that is going to tell tell and dictate how to actually draw that object. I'm going to go on my shaders folder, and I'm going to this time create asset, new folder, a fragment shader, and I'm going to call it write depth as well. I am simply going to connect it straight by drag and dropping it in the shader asset slot. And just to have a quick look of what this brand new default shader is doing, if I enter in code and now go to search my write depth shader, I can see that code's fragment shader and a vertex shader have been created for me. In the vertex shader, I'm doing some very standard stuff. Basically, the GL position is calculated using the vertex position multiplied by the model view projection matrix. This is a built-in uniform, and this is a built-in attribute as well. If I switch to my fragment shader, I can see that the fragment color, the frag data 0, which is the frag color, is actually writing a magenta color by default. All I want actually is to write the depth. So what I'm going to be interested in is basically only the GL position, converting my vertex position in screen space. I'm going to make sure that this guy is built, and now it is connected to my write depth material. If we go back in our view 3D, now we need to instruct that for this render layer, this object will actually use my write depth shader. I'm going to switch to shaded and wireframe so I can pick object easier. And I'm going to select with my object selected, I'm going to access the static mesh properties. And my static mesh basically have a default LOD. And as I expand this, you can see that now I have render layer and shadow, and I got my first primitive, and the material is now empty. Now I need to connect my material with this slot here. And if I switch to the other render layer, the one that is actually drawing the checkerboard, we can see that it is connected to the material checkers, which tells me that when I'm drawing on the render layer Untitled, for the primitive, my first primitive, I will use this material. And you can have multiple render layer here, and for each and every one of them, you can specify which primitive is going to use which material on this specific render layer. And as I click on shadow now, I am going to connect my write depth material to my first primitive, and as you can see, it's now actually drawing something. I can always speed up the process by simply drag and dropping around, and now I actually have something that is drawing on this render layer, only basically writing the depth, as I'm not doing anything, and I'll only have a depth texture attachment that is connected to my probe. Only the depth data will be filled. Now basically it is time to start setting up our set up our probe property that we left earlier. I'm going to do a little split here and move these two down here, and this is usually what I like to do. I like to have a view 3D upright to actually visualize what I'm doing. And as I create that view 3D, now my actual probe gets updated because I got this view 3D here that is, I got one over here that is in edit mode, and I got another one here that is actually drawing my final output. And as you can see now, I can visualize my depth texture, but something is not quite right because the camera setting of the capture settings are set properly, but the camera settings are not basically what I want. I do not want to use perspective. The shadow will look distorted, only looking from the point of view of the light, and that get distorted. I am looking for creating basically a directional shadow. So for that, I will switch my camera settings to actually use orthographic and zoom to have a flat projection. And as I do that, automatically I can see that it is changing. Using the line visualizer here, I am going to want to have as much the best resolution as possible, the best resolution of depth, the best depth range as possible for my shadow. And for that, I'm going to tweak the clip start and clip end. Let's say about 30. And as I do that, I start to already have a clear visualization of my depth buffer. For the zoom, I am going to tweak it to make sure that I'm actually including all my scene here. So, and I'm going to change the clip start to be as tight as possible from the beginning, and my clip end sounds about right. If I put it closer, it will actually start cutting. So I'm going to leave it at 30. That sounds like good values. Let's put it around value here, 19.5. And now I am actually ready to use that depth buffer and project my shadow onto my scene. Basically, the last thing that left now is to update our PBR shader to actually draw the shadow on screen. So we are going to go check on our second render layer, selecting an object, what is the actual material that this guy is using here. From the materials property, I set it manually, so I'm going to click this one to have it automatic, and I can see that now it is using the checker PBR, which is what we need to actually edit. We're going to need more precisely to edit the shader that is connected to checker PBR. So I'm going to go back in my code, and I am going to select my PBR shader. And you can see that now this shader is actually using nodes, and I'm going to want to basically code manually on this one. So I am going to toggle off the node, and accessing the code, I'm actually going to flush the code here to start fresh. And I am going to go search my vertex shader code over here, and now my fragment shader code over here, and we'll get started with that. First, the vertex shader. We are going to see that I have some, as you might have noticed if you're a bit familiar already with GLSL, I am currently using GLSL 2 for this shader, even if my actual core profile for this project is OpenGLES 3. As I click the build button, automatically my code from GLSL 2 will be converted in 3, but it would have been perfectly legal to just write in plain GLSL 3.0. So basically it makes also things more clear for this specific tutorial. So basically I'm having my vertex attributes here, my position, texture coordinate, normal, tangent. If you want to have the full range of the possible attributes that you can use, simply check the documentation on API and API documentation on the shader category. And we are having a bunch of built-in uniform here. We are having the normal matrix of the object, pretty standard, and we're having our model view projection matrix that is going to convert our vertex into screen space, very standard. And we're using here another built-in variable that is called GFX viewport, that is basically giving us the viewport boundary, the X and Y, and the width and the height. And we're going to need to have this information to calculate the texel ratio of our shadow map. Since our shadow map have a 1:1 ratio with our final output, we are simply going to use the viewport 1 divided by the viewport to get our actual texel ratio. Next, I am having a user uniform, which means that I am going to need to provide that information. And what it's telling me is, because I put a underscore here, every time a variable can be tagged. Every time you create a uniform variable, you can tag it that this one will not be set on a per object, per material basis. If you have a look at our object, at our material, sorry, and I did not recompile this shader yet, so it is basically using the last compiled one, which had these nodes, and inside the node we had a uniform variable that was called g underscore color created without that underscore. It means that this uniform can then be edited on a per material per object basis. So I can set that for these guys the color will be this, the color will be that in this example. But as I add an underscore, it means that I manually, using a script or a CC++ plugin, will have to specify that value. And this is what that underscore means. By putting an underscore, it will not appear in the user variable interface. Next step, we are having a few varyings that is going to help us to bridge from the vertex shader to the fragment shader. Jumping to our main function here, I am calculating the texel ratio, calculating my TBN matrix to be able to convert my vertex normal into tangent space later in my fragment shader. I am going to pass my texture coordinate to my fragment shader as well, move my vertex position into screen space, and I'm going to calculate the projector coordinate using the projector matrix, which is, as you might have guessed, basically the matrix from my probe, my point of view in space that is actually looking down my scene. And I'm going to multiply that with my vertex position to have my correct projector coordinate. If I jump to my fragment shader, I'm having a bunch of samplers, and these samplers are basically connected to my sampler slot here, meaning that they're all also built in. So sampler 0 is going to go search my base color, 1 my normal map, 2 my roughness, 3 metallic. And if you notice here, we're having sampler number 4, and sampler number 4 will actually be our shadow map, which we're going to add. To do this, I'm going to add a new sampler, select the slot, select the type of sampler, in this example texture, and I'm going to drag and drop my shadow right here. So now my sampler number 4, which is my shadow, will now be sent over to my shader. I have another user variable, which is sun direction, basically the direction of my light. These are my varyings that I send over from my vertex shader. I am having a function called shadow that is doing a percentage closer filter on the projected shadow. Jumping to our main function, we have the albedo, which is basically our base color, and I am moving my tangent space normal based on my TBN matrix. So I'm going to extract the normal from my texture here and then convert it in space. I am then requesting my shadow. That shadow function will basically return me 1 or 0 if there is actually shadow at that point. And I'm going to pass the current normal and the sun direction to avoid artifacts, shadow artifacts, and pretty standard all other type of not wanted problems that comes with actual shadow map, and this is all handled here, very standard stuff. And vector 3 ambient, what I'm doing here is adding a bit of color at the location where the shadow will be. Instead, the shadow, wherever there's shadow, is just going to be fully dark and no color at all, since my shadow function returned me 1 or 0, fully bright or fully dark. So basically what I'm doing here is I'm creating an ambient color and using the invert shadow value to actually add a bit of ambient when the point on screen is actually covered in shadow. And finally, I calculate my fragment color, which is my ambient plus my albedo, my base color, multiplied by shadow. I am going to compile now, and as I do that, something is wrong here. Basically, everything start to use my ambient color. It means that it's fully covered in shadow, and this is because we haven't specified our manual user-defined uniform variable. And to do this, what we're going to do is we're going to create a script that is going to be connected to our material, once again, on draw event. And we're going to update those uniform variable manually. Since I'm here under my material, I'm going to create a new thread script, open it up, and coming back to my library, I'm going to go on scripts and then asset and new script. And I'm going to call it PBR since the name of my shader and of my material and the shader is also PBR. I'm simply going to create the script like this. And in my code editor, I am going to now select PBR. Let me go search the code over. And I got my script that is here. We're going to explain it in a moment. And I'm pasting it here. And as you can see, it is responding to the onDraw function callback. Every time there's an event that you are actually coding event callback, there's going to be a variable called event. And event gives you access to everything that is going on within that specific event. As you can see here, I'm going to store my scene pointer to a local variable. And since I'm actually drawing my event is connected to a material, the event material is then available, and I want to access the shader because I want to update those uniform variable. So I'm going to store my shader as a local variable. Now I'm going to go search my sun object, which is basically called lamp. And to do this, I'm going to use one flavor. I got another flavor below that is basically a shortcut, but just to show that it can be done in different way and how easy it is to access stuff within that event callback, you simply have to do event.scene and then get object and the name of the object. And I'm going to store that sun as a local variable. Using my shader, I am going to call the function setUniformVector3 with the name of that uniform, which is sun direction. And accessing now the sun data, I am going to access sun.data.lightSource and the direction. This is what I need to send over as my uniform. And the direction here will be by default in iSpace for a question of convenience and also compatibility. Later on, when we're dealing with really PBR lighting, we will basically change that space to be in world space because it makes more sense while dealing with physical based rendering to calculate lighting in world space. But for now, we are going to leave it in iSpace so it will actually fit with our shadow map that we're having here. The next thing that I want to do is I want to update my probe projector matrix. So I am going to create a local object variable, and this time I'm going to call scene my local variable that have been extracted from event scene, and then get object and my probe. I am actually interested in the projector matrix. So there's basically two ways to do this. You can either calculate it manually as I'm doing here, but internally it is calculated the same if you want to do something else on it, in example. So basically the projector matrix is the multiplication of a bias matrix that is basically a identity matrix that is biased at 0.5 and our dynamic probe camera projection matrix and the view matrix of that camera. And while we multiply these two, we're going to end up with the projector matrix. Another shortcut to get access to it, we get access to the projector matrix by accessing the probe object data probe and then get the capture. And our capture was our basic -z plane here, and this is the one that we're going to access. If, like I was mentioning, if you have access to, if basically your probe is a cube map, you will have access to all faces, but since it's a plane, we only have access to our -z. So the face of the capture that we're looking for is basically my -z, and I'm going to access the projector matrix property, which will then calculate my basic projector matrix, basically the same operation as this, for free. And now I need to actually tell to multiply that projector matrix with my current object, because each and every object are basically placed at different location, and I need to multiply that projector matrix with the object world matrix, which will give me the good space where both of them can be then calculated and accurately projecting my shadow on screen. And finally, using my shader, I'm going to set the uniform matrix for my final projector matrix that is going to help me to calculate that shadow on screen. As I do this, before hitting the build button, I am actually going to drag and drop that script onto my script slot here. So as soon as it is not built actually right now, it is not responding to any event yet, but as soon as I'm clicking the build button, voila, I start having shadow on my scene projected correctly. Our shadow is now implemented, and the next step will be to implement PBR lighting. We are going to start by updating our PBR shader to be able to calculate the lighting in world space. So we are going to update built-in uniform. We're going to add built-in uniform and add also extra parameters that is going to allow us to calculate that lighting in world space. These updates will include a user-based variable, so we're going to need to update our PBR script to actually send this data over to our shader. Next, we're going to actually implement our lighting calculation, since we're going to have all our variables ready. And finally, we are going to do a final tone mapping that is going to convert from linear space, where we actually calculate this lighting, and convert it back to gamma corrected. For the first step, we are going to create new uniform. We're also going to need our world position of each vertex, of our vertex on screen, and we're also going to need our camera, the actual camera position in world space. We're also going to update and send over to our shader our actual sun color multiplied by its intensity. So later on we can simply change that color or that intensity, and the changes will be reflected directly. Since we have now user-based variable, we're going to update our PBR script to actually send that actual sun color and that camera position. We're then going to calculate our lighting equation. We are going to fetch finally our metallic and roughness value and pass it over to our lighting function. We're going to convert the actual base color that we already have and convert it to linear space, where we are going to actually calculate our lighting. Since all our texture, we only have basically one, our base color is already gamma corrected, it is very important to convert it back into linear space before we are actually doing the lighting. And finally, we're going to implement our lighting model functions, and this is basically the result that we're going to end up with, which is in linear space. The final step will be to convert the result from linear space to gamma space, applying tone mapping. And our basic final result will be converted from this to this, where we have basically our light and our shadow that is properly calculated, just as we did in the previous section. With our shadow implemented, we are now going to move on and implement PBR lighting. Our lighting will be calculated in world space. So the first thing that I'm going to have to do is to actually update my PBR shader to take that into consideration. I'm going to first create a bit of space here, move my outliner on this side, and the ME, we're not going to need to use it, since we're basically only focusing on our sun, our lamp, our sun named lamp. We're going to delete the ME. We're not going to use it for this tutorial. I'm going to jump in for inside my PBR shader and ensure that vertex shader is actually selected. The first thing that I'm going to do, I am going to implement a new built-in uniform that it's called GFX model matrix. What GFX model matrix is basically the world matrix of the object currently using the material. So this will allow me to create my world space position of my vertex by using the world matrix multiplied by the current vertex. I am going to have that world position, and I'm going to first create a new varying because I'm going to need to bridge that position to my fragment shader from my vertex shader, and then I'm going to calculate this position, which is basically simply our model matrix multiply by our current vertex. Since I'm adding a new varying, it is very important to append it in the list of the varying inside my fragment shader so I can have access to it. The next step will be to create a new built-in variable that is going to a 3x3 matrix that is going to allow us to convert from eye space to world space. If you recall in the previous section when we were implementing shadow, by default our sun direction is returned to us in eye space, and we're going to need to convert that direction. So by multiplying this direction vector with our view matrix inverse transpose, we're going to end up having our world direction for that sun. And we also have normals to take in consideration. So we are going to apply that same conversion on our normal calculation after we call our shadow. We have now that conversion matrix implemented, and we will also add two new user variable. Basically, the first one will be for the color of the sun. That is going to be the color multiplied by its intensity. So as soon as I change its color or its intensity, it would be reflected directly on my output. Another thing that I'm going to need is actually the world position of my camera here to be able to calculate my lighting properly. So I'm going to add these two new uniform to my fragment shader. And since they are user variable, I'm going to need to update my PBR script as well to actually send them over to my fragment shader. So basically this involves to send my two new uniform here. The first one is my sun color, and I am using vector mat to basically calculating the result of the intensity multiplied by the color that will then be sent over to my fragment shader. And I need to update my camera position, so I'm going to use my current event camera because that's the one that I'm actually using to render my untitled render layer, and I'm going to get access to its underlying object and world matrix, and I am simply going to use a little helper that is going to send me the XYZ location of this camera down to my fragment shader. I am going to build this script, so it's already trying to send our sun color and camera position, but we did not rebuild yet our PBR shader, so they are not taking consideration at this point. As the little star here near the name can tell us, it means that the script have not been recompiled. So next step will be to jump inside my fragment shader, and under the shadow function that we implemented in the previous section, I am going to now implement a bunch of new function that is going to allow me to calculate my actual lighting. If we have a quick look at it, we are having basically function for our normal distribution, our geometric factor, and our Fresnel. And we have that little function here that is our PBR lighting that will take the albedo color, our base color, and the light color that we have sent over to our uniform, in this case, the metallic value, the roughness, our normal, the light direction, and our view direction. Back in my main, I am finally going to access that metallic and roughness value that I've been ignoring actually since the beginning of this tutorial, I'm first going to delete the albedo and I'm going to replace it with this. My albedo will now include this operation that is going to allow me to convert my gamma corrected base color to linear. It is very important to convert gamma corrected color values down to linear. Instead, our lighting calculation will be wrong. And I'm going to use the default gamma value of 2.2, which is pretty standard with most monitor. And that is going to return me my albedo value, my base color in linear space. I'm then going to extract my, if I go search my PBR material here, I'm going to then extract my metallic value from my third sampler and my roughness value from my second sampler. Now, under shadow, I'm going to give a bit of space to actually implement the whole lighting calculation. I am going to copy and paste this code that I do not want to convert my normal back to world space before I have done my sun calculation, so it have to be done after. Same for my sun direction. My normal and my sun direction have to be converted after my shadow calculation, which is actually an eye space. So basically I'm going to convert my normal back into world space by multiplying my view matrix inverse transpose by this actual normal. I am going to normalize my camera position minus the position of my vertex in world space, which will give me the view direction. I am also going to calculate the reflection vector that I'm going to use in next steps when we're implementing radiance, and this is basically a location to the most obvious location. Since we're all calculating those view vector and we already got the data, we calculate the reflection vector here. Now my light vector is going to be my sun direction, which was given to me in eye space, multiplied by my view matrix inverse transpose, and maybe we can actually invert that just to be more consistent here, and this is going to give me my light direction. And finally, I'm going to calculate the radiance for this specific light, in this case my sunlight, by passing my albedo color in linear space, very important, my sun color, metallic value roughness, my normal in world space, my light direction in world space, and basically my view direction, which is also in world space. Everything here is in world space, so the lighting calculation will be effectuated properly. Now, since I am dealing with linear space now, I'm going to need to tweak a bit my ambient value here, because this was actually the value, the default ambient color gamma corrected. So I am actually going to change this by adding multiply by 0.1 just to balance, and all this will be actually replaced in the next two section by implementing the radiance, which is basically the specular term of the ambient, and my irradiance, that is my diffuse term of the ambient. So this will totally be replaced in later steps, but right now we're only focusing on PBR lighting. I am going to create basically a new color value that is going to be my ambient color plus my radiance of my light multiplied by shadow. And now I need to basically tone map, gamma correct these value because they are in linear space now, and I need to convert them back into gamma corrected space so they display properly on my screen. For that, I am going to implement simple HDR tone mapping, and I am going on my color, my linear color here, and I'm going to send back that fragment on screen. And now, since we're ready, I am going to build, and now we have PBR lighting implemented for our scene. With our PBR lighting up and running, we are going to start by implementing radiance to have our image-based lighting up and running. This is basically the final result that we're going to achieve, mixing the existing shadow plus PBR lighting and our first term, our first ambient term that we will calculate will be the specular term, which will be our radiance. For that, we're going to first create a cube map using our texture that we're using for our horizon. Then we are going to implement environment approximation to be able to calculate the BRDF for our current reflection vector. And we are going to apply that to recalculate our ambient term. The first thing, create a cube map. We're going to use the built-in tools from the editor to put on each and every face of our cube map our existing texture, creating a seamless cube map. We're then going to proceed with our environment approximation, converting our cube map that is gamma corrected back to linear space, since it will be part of our final lighting calculation, and we need to calculate it in linear space. We're going to convert it, and we're going to run our environment approximation function. As a result, by having the radiance specular IBL term passed to our function, this is basically the final result that we're going to have, mixing the two. And finally, we are going to use the step that we have done previously, our PBR lighting result plus our radiance result, our specular term of the ambient, will give us this final result. We are now ready to implement image-based lighting. Basically, image-based lighting will have a direct impact on our final ambient color that will then be added to our radiance. Since the beginning, we have been tweaking that ambient value as we see fit during the last two sections, but it is now basically time to really put it in place by calculating the radiance and the irradiance. The first thing that I'm going to do is basically calculate the radiance. The radiance basically for me have the most impact on the scene. It give basically the amount of reflectivity a specific surface have, and how much the color, the resulting color of that reflection will have, how much impact it will have on the surface. So basically, to do this, I'm going to need to create a cube map, and I already have my skybox here that is going to provide me all the necessary faces to actually create that cube map. For this, I'm going to go in textures and asset, new cube map, and of the type static, since all my textures are basically static texture. So positive X will be on my right when I'm looking down that skybox. My negative X will be left. Positive Y and negative Y will be in front and back of me, so front and back. And finally, positive Z and negative Z will be on my top and bottom. So top and bottom. And basically what I'm going to try to do here, as you can see, I got my cube map generated. What I'm going to do here is I'm going to use my roughness value to drive which level of detail will actually be picked on that cube map. So for that, I'm going to need to modify the minification filter and create mip-map. So by dragging the level of detail, you can see that it is getting blurrier as I increase the level of detail. And this is what we're going to do to calculate our radiance. We're going to basically approximate the BRDF, because there's no real lighting in a point like in space. Basically, we're going to do an approximation of that BRDF based on our reflection vector and our view, and we're going to use the roughness to actually drive which level of detail will be picked. I am going to create that cube map, and I'm going to make sure that my checker PBR is selected inside my material properties, and I'm going to add a new sampler here, which is going to be my cube map that we have just created. So create a new slot, select it, and this time the type will be cube map, and I'm going to drag and drop my cube map asset here. Similar thing as we did with the shadow earlier, but this time the type was a texture, a two-dimensional texture. This time we will use a cube map. Now this is set up. We're going to jump in our code and select our PBR shader and ensure that we are in the fragment shader. At the top here, my samplers, I'm going to need to implement my sampler number 5. So I'm going to do that right away. Uniform sampler cube this time, because we got a cube map, and sampler 5. And now I am ready to actually start changing that ambient value. I'm going to jump to my main function, and just before that I am actually going to implement a function that is going to allow me to approximate that BRDF based on my specular color, my roughness, and the dot product of my normal and my view vector. At ambient, now going down in the main function, I am totally going to replace that ambient calculation once and for all, and we're going to add more later when we're going to calculate the irradiance. But for now, the radiance, I'm going to get rid of this one completely and start basically calculating the final value. What we're doing in this new block of code, we are calculating our normal dot view vector. We are going to calculate the reflectance at normal incidence, and to do that we are going to mix basically our albedo, our base color, with our metallic value, and the 0.04 is basically used as a default value for all dielectric material. We're going to calculate our Fresnel based on our normal dot view vector. We're going to use that reflectance at normal incidence, and using our roughness we're going to try basically the final Fresnel value that we will use on to approximate that value that the BRDF value that we're going to grab from our cube map. So basically take note that if you want to implement image-based lighting properly, you should use convolution filter on the cube map that you're going to use for radiance and the cube map that you will use for irradiance. There's already tools out there that is doing this for you, but just to keep things simple and to stay within the NRG environment, we're just going to fake it a little bit and simply use our MIP map level, which will still give us decent result, but it could be basically better. So what am I doing here is I am picking a level of detail based on my roughness using my reflection vector that we have calculated previously, and this will give me the color at the reflection vector. I am going to use that color to drive my specular, which is basically my radiance. So my pre-filtered color that I have multiplied by my environment, my BRDF environment approximation, which is my Fresnel value, my roughness, and my normal dot, my view vector. And I'm going to start by assigning that to my ambient value. We're going to need to later on, when we're calculating the irradiance, we're going to need to add that specular term to our diffuse basically. But for now we only have our specular, and we're going to assign that as ambient to get started. In a similar fashion that we have done in the previous two sections, we are going to actually cool down the level of our shadow to make sure that is going to stay in lower range to still have like an ambient color. Instead it would be simply 0. So basically we're calculating the shadow on a factor of 0.3, which was actually the color that we used earlier. So basically we're going to make sure that the ambient color, regardless if there's shadow or not, will stay around 0.3. And finally, no changes here. Apply the ambient plus my radiance that I calculate from using PBR lighting earlier. And as I click the build button, you can see that right away it have a huge impact on our scene. Our coloration completely changed, and to be honest, our scene starts to be a lot more realistic. Take note that I actually clamp the level of detail that I'm going to pick to be from 0 to 4 here. If you go down more than 4, it starts to be basically way too blurry, and we still want to have something that it's actually more reflective than this. You see, as I go at 5, it starts to be like unrecognizable. So 0 to 4, 48256 by 256 cube map is basically a good value to get started. And as we are moving our camera, we can see that now we start having reflection. We can start seeing our sun here, over there, and if we are looking at down at the floor, we can and close up, we can see that we are having basically some reflection of that sky that is also those clouds up there that are basically reflected, like in this example here, on our floor. And that basically conclude the way we are going to implement basically radiance. We basically have now our ambient specular term that have been calculated, and to continue our quest to implement fully image-based lighting, we're going to need to implement the irradiance. The irradiance, that is basically the ambient diffuse term, how much the environment around a specific object affect the coloring of that object. For that, we're going to calculate the spherical harmonics, second degree spherical harmonics, that is going to allow us to apply, to evaluate, approximate this ambient coloring, and then apply it onto our object. So the first step will be to calculate those spherical harmonics. The second one is to apply them into our calculation, and finally recalculate our final ambient term with both specular and diffuse. To calculate our spherical harmonics, we're going to create a full screen pass off screen that is actually going to calculate this second degree spherical harmonics using our existing cube map. The result will be basically a 3 by 3 RGB values that, once enhanced, will look pretty much like this. Once we have calculated those spherical harmonics, we're going to need to extract them and apply them. The step to apply and extract those spherical harmonics will involve to first create a utility script that is going to allow us to gain direct access to the text cell of the off-screen texture that we have calculated in the previous step. We're going to then extract those spherical harmonics from that texture and update our PBR shader. As a result, once applied, those spherical harmonics will have this direct impact on our scene. Once we have that, we can then recalculate our final ambient term, that is going to be our shadow, our PBR lighting, and our radiance that we have calculated in the last step, plus our spherical harmonics that we're going to calculate in this step, that is going to give us the diffuse term of the ambient calculation. And then all of these apply will give us our final result with PBR lighting implemented, with shadow and image-based lighting. We are now going to finalize our image-based lighting. In the previous section, we have calculated basically the specular term just because it have actually more impact on the scene itself, and we can have like a direct feedback from it. This time, we're not only going to calculate the irradiance, but we're also going to learn a new technique that is going to allow us to render full screen, a full screen quad, for either post-processing effect or other type of off-screen calculation. We are basically going to create a new layer with a camera, assign a frame buffer settings, and render to texture the calculation of that pass. The first thing that I'm going to do is I am going to go on my scene properties, and I'm going to add a new layer. And for the irradiance, we're actually going to calculate the spherical harmonics. We could have as I mentioned earlier, the full IBL way and post-process both our irradiance and radiance cube map. But we're going to keep things simple while still implementing a new technique. So basically what we're going to do, we're going to create an off-screen pass that is going to calculate our spherical harmonics. I am going to call this shader SH for spherical harmonics. I am going to go in edit mode for that render layer, and I am actually going to create a new camera perspective. and I am going to change that object name to be SH as well, just to be more clear. I am going to go select it, and you can see that now basically I have two cameras. I got my default camera that is rendering my untitled scene, and now I'm going to select my SH camera to be binded to this render layer. The last thing that I'm going to fill in is basically the material that is going to be used to do that off-screen processing, and this will cause a full screen quad to be created as well. So the next step that I'm going to do, I'm going to go on the material and asset, new material that I'm going to create, call SH, and create. I am going to drag and drop my SH to this field, and as you can see now, I lose my editing mode, because basically I am rendering a full screen quad right now. It doesn't apply anymore. There is no real geometry that is drawn on that render layer, including the camera. The camera is actually a full screen that is then projected. So there is absolutely no type of object or geometry that will be displayed on this render layer. It is strictly set up to be used as a full screen render pass. And now I'm going to start to edit my material here. I am going to drag and drop it, and I'm going to create a new shader. Asset, new fragment shader. I'm going to call it SH as well, just to be consistent, and I'm going to drag and drop it into the asset shader asset slot. I am going to then create a new sampler, because our spherical harmonics will be calculated by taking each and every face of our cube map and analyze the spherical harmonics component for each and every of these faces that we will then be able to reconstruct using the normal in our PBR shader. So I am going to set up a cube map, and I'm going to go search my main cube map that I'm going to place here, and this is the one that we're going to use to calculate basically those spherical harmonics. Next, I am going to go in with my SH camera selected. I am going to go in my camera properties, and this time I'm going to enable my frame buffer. It is not only a regular camera like our default camera for the untitled scene. This one will allow us to render to texture, and we are going to create a new attachment where the result of that post-processing will be located. So under the textures directory, I'm going to go in asset, new texture attachment, and this time I'm going to call it SH as well, and this time I'm interested in the RGB color, because all of these spherical harmonics will give me a RGB color. And just to have a good level of precision, I am going to use a floating point texel. Basically it is only used for post-processing. As a processing phase, I will then create a utility, a tool that is going to allow me to extract the information from this texture. So first off, I'm going to create my SH texture attachment, and I'm going to drag it into the first color slot here. I'm going to go back in my code, and now I'm going to start adding to my spherical harmonic shader. The first thing that I'm going to do is I am going to implement a vertex shader that is going to allow me to have basically a texture coordinate for that quad. As it is basically a full screen quad, I am going to convert the vertex position, bias it to make sure that my texture coordinate will be in the range of 0 to 1, basically triggering each and every texel of that texture, that offline attachment. Inside my fragment shader, I am first off, before calculating the spherical harmonics so you can visualize better what this procedure is actually doing, I'm going to copy this code here that is basically the default shader toy code, I believe, that is basically taking in consideration the current texture coordinate, and I am having a new built-in uniform here that is called GFX stats, and this gives me time and frame information in my vertex shader. It is a vector 3. The X give me the delta time of the frame, the Y give me the application time, and finally the Z give me the current frame number. So you can use that in your fragment shader for time value, updating things over time in your fragment shader. And what I'm going to do is I'm going to build first that script, that shader, and I am going to enable here my spherical harmonics render layer. And as you can see here, my texture have been updated. If I preview it to have a larger preview, and this is basically what I'm rendering off screen. And as you can see, there is no effect on my main scene that I'm drawing because it is done totally in the background, totally off screen. What I'm going to do is I am basically going to save my project because I'm about to push the play button. By pushing the play button, it is simulating the application that is actually running. So I want to first make sure that I'm saving all this so I can push the button and play. And as you can see now, my colors start changing over time since my application time is increasing. As I stop, go back to 0, this is my 0 value. Now, what I'm going to want to do here is do some little tweak to that texture. We don't need that texture to be that big. Basically, spherical, second degree spherical harmonics are basically 3 by 3 only, giving me basically 9 values. So I am going to go in my camera, my SH camera, and I'm going to change the resolution of that texture to be actually a fixed size. And I'm going to set it to be 3 by 3 because I don't need much more than that. And another thing that I'm going to want to do is I am going to click that little lock here. By default, every render to texture attachment are locked, meaning that all the text cell will strictly be held in GPU memory. But in this case, I want to calculate those spherical harmonics and then have access to them locally. So by unclicking that little lock, it will actually copy the text cell value from GPU memory to local memory. So I can then run a utility script, a tool that is going to allow me to grab that texture and then read each and every text cell data that is contained into that texture that have been rendered strictly on GPU. Now, if I'm doing this, first thing that I'm going to do now is I'm actually going to turn that off because my code here will start to be very GPU extensive. Calculating the spherical harmonics is somewhat of a big operation, and I'm going to go search my spherical harmonics code. I'm going to paste that into my fragment shader, give a bit more space here, and basically this code will go in each side of my cube map and start calculating my spherical harmonics. Since I have now my cube map that is connected to that material, it will then be sent over via my material, and my fragment shader here will be able to pick it up. I'm going to build that code, and I'm going to click only once and quickly turn it off because it is very expensive. And voila, basically I have my spherical harmonics that are calculated here. So now how are we going to use this value to actually how we're going to use these spherical harmonics value to be used inside our shader? What we're going to do here is we're going to create a utility that I'm going to place on script. Utilities are basically scripts that only run in the editor. They will not be published. They are basically just tools that can use the IDE API, the theme API, or the graphical user interface API. In other words, can only run in the NRG editor environment. Once you're publishing your application, only the NRG core API, the one that actually the NRG editor is talking to, will be actually available to you. So basically, I'm going to start editing that utility. I'm going to go under script and utility, and I am going to copy that little piece of code here that is allowing me to read back my Texel data that have been computed on GPU. This is a standard utility header function that is called register, and by default the system will call that function to actually execute the tool. So I am going to go search manually using my library API. I'm going to go search my SH, spherical harmonic texture, and for each texel on the width and the height, I will then go search my spherical harmonic value as a floating point and then print that value on screen. So this will allow us to then have these value in the console and go copy and paste them inside our PBR shader, which I'm going to do now. I'm going to run the script once, the utility once, and now I'm having those spherical harmonics value available to me. I'm going to go back in my PBR shader and make sure that my fragment shader is now selected. I'm going to jump down near my main function, and I'm going to implement a shader function that is going to allow me to extract back those spherical harmonics, which is called get spherical harmonics, and it takes in parameter a normal. And you can see that here I am having an array of vector 3, and this is the information that I'm going to fill in right there. Here I am going to fill the array with the value that I have calculated. If I get rid of this, I have my full array and I'm ready to go. Now, the last piece that we need to update is finalizing our ambient code for image-based lighting. We have calculated previously the specular, the radiance factor, and now we are going to be good to calculate our radiance factor. And for this, we're going to use that simple piece of code here to first get our spherical harmonics, and second, we are going to modify our ambient to use within its calculation our newly calculated irradiance. I am going to replace the ambient here. So basically what we are doing here, we are getting our spherical harmonics based on our world space normal, and we are calculating now the diffuse, which is basically our irradiance multiplied by our albedo, our base color. Now, to calculate our ambient properly, we have to calculate the metalness, the metallic factor, as if you would call it, of our basically of our surface, using the inverse Fresnel value and the inverse metallic value that we have previously gathered. So the result of our ambient will be the metalness multiplied by our diffuse value, our irradiance value, plus our specular value that we have previously calculated. So in order to see exactly what these spherical harmonics will have as an impact on our scene, I am temporarily going to comment our basically radiance, our light calculation here, and I am going to keep only my irradiance, getting rid of my irradiance data here, and I'm going to run that, and right now you can see that basically I am having a, if I run that here, these are basically the spherical harmonics that are applied on my scene here, strictly the spherical harmonic, which gives me basically an overall color of what is basically reflecting around me in my environment, but not in a reflective way as the radiance that I calculate, that it really used the reflection factor. It is basically an omni hemisphere that is basically picking up the color facing the direction of my surface. As you can see here, it is relatively orange, and if I look around here, this is because my skybox here is orange. If I look more up, I'm having that kind of light blue gray, which is giving me basically what is up there here, an agglomeration of all these colors packed together. Now, as a final phase, we are going to reconstruct our full equation. I am going to uncomment that. So my ambient will now be my metallicness multiplied by my diffuse plus my specular. My ambient is then biased to make sure that my shadow will not be too dark. And finally, my final color will be my ambient plus my PBR light and multiplied by my shadow. I'm going to run this, and we have basically our final result using shadow, PBR lighting, radiance, and irradiance image-based lighting.